Uh, okay, so welcome everyone. The first meeting on quantum dynamics and overview. It's a work in progress title. Okay, it's maybe it will change at some point, but for now it's what it is. So let me start with some organizational bits. Okay, so first of all, here is a lecture notes which I am working on right now. So this is a work in progress, okay? So it will change from week to week. I'm all into that. So basically, I will try to follow the what I will be saying. It should follow very closely to what is written here. And if I say something that is not written here, I will probably change the notes to reflect that. Okay, unless the things I will say will be something not worth noting down. And the notes themselves, there are a couple of things about them. So the instruction, how to use them, okay? So you have to be able to read in English, of course. And there are like a couple of things. This segments with a thick bar, this is a kind of like a mathematical aside, okay? So this is like something that you can skip if you don't feel like listening to some detailed explanation what the vector space is or something like that. And the other thing is there are assignments here, like this. Okay, there is assignment. So I will be when I say okay, let do assignment number X. That means it's an assignment number X from the notes. It's not like I won't be checking your homework. Okay, this is like for your to have some hands-on experience. And every assignment, this is my pledge to you, it has a solution. Okay, so you don't even have to do them. Just think about it a bit. Try doing something if you wish, and then just look at the solution, because there's probably will be some maybe interesting comments in the solutions as well. And to get to the solution, you can just click hyperlink here, and it just transports you here. Okay, and you can go back. So this is how it works right now. So these are the notes. Where do you get those notes? It's probably a good question. So there is a thing. There is a website of our division, theory.ifpan.edu.pl, and there is a teaching here, teaching page. Come on. What's going on? What's going on? Oh, that's peculiar. I don't know what happened. So teaching, and you can, here it is, quantum dynamics. And you see, there it is. Here's the link, okay? All the info that you can wish for will be here, okay? So links to YouTube videos will be here, all the materials for reading. If I will be referring to some paper or some book, I will put it on the list here. And if it will be semi-legal, I would also put in PDFs there, okay? But the notes are here, okay? So that's the website. Let's go back to where? Now here. Okay, so this is it. Other stuff, if you care about zaliczenie, credit, there won't be any exam, okay, at the end. I don't do those. I don't believe in those too much. So it's basically everyone, attendance, okay, you have to attend. However, there are YouTube videos. So there is no way of me proving that you haven't attended by watching the YouTube. So in other words, you are, it's, automatically everyone passes, okay? so that's less work for me, okay? And hopefully you will not use this fact to your advantage and, like, I don't know, do something crazy here. Okay, so that's is this whole organization with YouTube video. I mean, that's maybe not of interest to you, but I will be trying to, edit the videos so that they come out the same day as the lecture. Okay, so on the Wednesday, we will see how this will go. I will try to do it like very fast. Anything else? Any questions about the organizational stuff? Okay. So let me begin with some preface. Okay, so like what is this lecture about? Okay, so the basic like a principal subject of this lecture is will be evolution operators in quantum mechanics in their variety of forms that you can find them. So we're talking about evolution operators, maybe evos. Is it a good like shorthand? Maybe evo, eva. Sounds cool. Evils, okay. Evas, evangelions, okay. And the things. So evolution operators. So things like something you probably well known to you. This classic exponent, but also more complicated stuff like beasts like this. Time-ordered exponents, stuff like that. But maybe even something more crazy, like not evolution operator, but evolution superoperators. Why not? We'll see. Or maybe even we go full on and do some green functions. So stuff like this. Z, T, Z, identity minus H, resolvent, dz to pi I. I don't know if you have seen this kind of beast, but this is also an evolution operator, okay? So stuff like this will be our subject. And our goal will be to like figure out or to showcase ways to calculate those guys, to compute them, to have some form that can be analyzed, can be touched, can be used, but in such a way that we don't touch any numerical methods. Okay, it's all done by hand so that you can see the stuff. No tables of numbers for us. We don't play in this kind of stuff. We want to do it by hand, basically. So what this means for us, it means that we will have to engage in some kind of perturbation theory. Okay, so we want to calculate evos, evangelions, our evangelions, but we'll be using the perturbation theories. Perturbation theories. This will be our tool. What are those perturbation theories, you ask? When you engage in that's good. Okay, whatever. So when you engage in perturbation theory of some kind, there is, like in a nutshell, the first thing you do is like figure out some kind of procedure, some kind of procedure for generating terms for your perturbation theory. So you figure out some procedure, whatever form it takes, to generate a sequence of terms of increasing order. So let me write it down and I will explain what I mean. So term of zero order, term of first order, term of second order, and hopefully you can go up to infinity, up to infinite order. what is the exact nature of those terms? That depends on your procedure, what you are doing. These are some functions, some numbers, some operators, whatever. Depends on what you're doing. What does it mean that it's of order? So when we say that the term is of order k, let's say it's a k-order term, what we mean is that the magnitude of this term, the magnitude, scales like a k power of some parameter lambda, let's call it, that quantifies how strong or how weak is like the thing that perturbs our system of interest that we are analyzing, okay? So this lambda parameter is usually so this is like a strength of perturbation. And it's typically assumed that it is small, something less than 1 at least, okay? So that the higher power of lambda is smaller than the lower power of lambda, right? 1/2 to squared is smaller than it's smaller than 1/2, right? So that's why you get those terms of higher. So it means that those terms we are generating, the higher the order, the smaller the term. That's basically what we are trying to achieve. Like the typical way mathematicians denote this, that the thing is of order k. There are a couple of standards. One is like you say that, okay, uk is, you use this kind of tilde of, let's say, lambda k, okay? The other way is to use the big O notation. Probably you heard about this. So you say that UK equals big O of lambda k, okay? And all these guys, what they actually mean in real terms, it means that the magnitudes of UK, so this is the notation for so-called norm. So norms are the mathematicians called functions that are used to quantify the magnitude of stuff. Now, depending on what the stuff is, the norm is properly adjusted. For numbers, it's just absolute value. For vectors, it's something else. For operators, something else. There are choices you can make. But you say that the norm is bounded by certain constant c and the lambda k. Okay, so big O notation, it basically means something like this. So this guy, term of order k, it scales as fast as the power of the parameter. Okay. Next, okay, so we generated our terms. Okay, what do we do with them? So it's kind of, we assume, we hope that when now we take those terms and just sum them up, so calculate a series made of those terms, and we do the sum up to infinity. We sum up all the orders, that we will recover the exact thing we want to calculate. So exact evolution operator we are interested in. So the assumption is that, so for example, let's say, let me do it like this. So let me define capital U, which is a partial sum of our terms. Okay, so this is a partial sum, and our assumption is that, for example, this kind of evolution operator, H plus lambda V, so this would be our perturbation. Lambda is the strength, assuming it's small, but this guy will be equal to the limit of n going to infinity of our partial sums, okay? Which will be, conventionally, it's denoted by this symbol. Okay, that's our assumption. We generated all the terms, and now when we sum them up, or because actually this kind of infinite series, maybe it's pedantic, but it's kind of important when things get complicated. That it doesn't mean that you really are doing the first term, add the second, third, fourth, and you go up to infinity, because this is not something you can actually do. But this is a limit of partial sums. Okay, so this is not really a sum, it is the limit of sums. Okay, this is maybe pedantic, but it's a huge difference, unless those terms are they behave well enough, when then only then you can say that there is no difference between those points of view. So this is our assumption, okay, that we generated our terms, and we take the series, full series, we get our exact result, which, for example, this evolution operator like this. And of course, calculating this kind of series, this full series, this limit, is as difficult as calculating the evolution operator in the first place, right? And this is too difficult. If it wasn't too difficult, we wouldn't need the perturbation theory in the first place, right? So we assume that if we did that, we recover everything, but this is not what we will be doing, okay? We will be doing some approximations, right? We don't want to sum everything. We want to construct some scheme that will allow us to sum only, let's say, couple of terms, but in such a way that it will be the difference between exact result and the thing we are constructing will be somehow maybe small. That will be good, so that we have a good approximation, so that our thing is very close to the exact thing, and we don't have to calculate the exact thing. We just need to calculate this our finite thing. So, for example, the simplest thing you could imagine is to just take this series and just truncate it on some finite order. So the simplest example of approximation, approx. So we say that this guy here, that is approximated in some sense by a finite sum. 0 plus 1 plus, let's say, un, which is, we already have a notation for that. It's a partial sum. This is the simplest thing you can imagine in this setup, and of course, this is not the only thing you can do. Okay, there are way more advanced ideas that you can do. For example, sometimes you can be so ambitious to like sum up to infinity, but some sub-series. Okay, not the whole series, but maybe sub-series. Maybe you can figure out some pattern here where you can, do some crazy inventive things and just formally sum up infinite number of terms, but not all of them. Okay. So so to give you some kind of example how this whole approach works. So probably you heard about Feynman diagrams, right? It's very famous. Whole particle physics works on Feynman diagrams. Okay, so for those who don't know, so there is in particle physics, so the things they ostensibly test in some accelerators under Geneva or something. The bread and butter method, basically the only thing they do is they do some perturbation theory. That's everything they do. Whole particle physics is a perturbation theory. Okay, so this is a big deal. And the procedure for generating terms, okay, this is what Feynman diagrams are. So the procedure is like it's a very clever thing invented by some people, and Feynman was there also. It's like you draw some pictures, okay? For example, you draw something like this. So that would be like, let's say, U1. You could have another picture, let's say something like this. Okay, you might, maybe this is U2. Well, it's not U2 because there are more terms. You have to add more pictures, which I don't know what else you do here. I'm not a particle physicist, but there are more diagrams of second order. So there is something here. Okay. And the thing is, so there are rules how you want k order, what kind of pictures you have to construct. Okay, there are some rules. They come from somewhere. It's not like completely random. Those rules make sense. And moreover, this picture, this silly picture, it actually translates into some horrible integral. Okay, some horrible stuff underneath. Sometimes it diverges to infinity, but there are methods for dealing with that. So this is a picture that human can understand. So this can be the core of our procedure. There is some rules for translating into horrible math, so that you can actually calculate something, and you do you sum them up, right, to get your basically evolution operator, or in a green function variety in this case. So something like this. Okay. This is sum up diagrams and you get something like this. And there are tricks, so you can truncate it. So let's say you get this diagram and this diagram, and you neglect everything else. That would be one way to approximate. But there are very clever guys where they like, for example, you can notice that this diagram and this diagram they are kind of similar, because if you like cut here and here, this would look like this guy, this guy, this guy, this guy, something like this. And you can like imagine higher order term, you would like stick more of those guys. So you can imagine that you have like whole infinite series of guys that look like this. So there is a pattern here. Okay? And it turns out that there is a way to...
Is it so that every second diagram is built actually this basic one?
I mean, the way they write it is like, you write it as... if you rip out this guy here, you know what? That's too much detail. Too much detail. I don't want to get into, because I am tempted to like go. But that would be yeah. I mean, the thing is that when you have like a repeating fractal pattern, they figure out how to sum it up. Okay, fully sum up all the infinite chain of this kind of guys. Okay.
At some point add anything inside that doesn't change the outcome.
Yeah, there are some. Yeah, I mean, there are some rules and so on. So truncating series is one thing, but there are more, and perturbation theories is a whole art form, right? And there are whole subfields of physics that are perturbation, some kind of perturbation theory. Okay, so this is like, so that's why it's kind of, I guess, important to know something about it. Okay, so hence this course. So what else do I want to add? Okay, so two more things when you engage in this kind of behavior, like doing perturbation theories. So one thing, so you have your procedure for generating terms. It can be drawing diagrams, it can be whatever. There are many ways to do it. And this procedure is not always, but often is some kind of like iterative equation. So it's like maybe you generate like a first order term, then there is some way to build out of it the second order term, and then from first and second you do something and you get third term and something like that, right? And even if your procedure is convergent, in a sense that you can calculate using your moves here a term of arbitrary order in a finite number of steps. Okay, so like you want term of order 7 billion. Okay, here is how you do it. It will take only 60 years to do it, but it can be done. So even if your procedure is convergent, there is no guarantee that when you sum them up, you will get convergent series. Okay, this is possible, or at least it won't be convergent in a robust enough way because there are different types of convergence. That I am describing asymptotic series basically. Maybe we'll talk about asymptotic series at some point because it's kind of cute topic as well. So it's like typically once you have your terms, your diagrams or whatever, like the first order of business is to like investigate the convergence of your series, okay? And does it converge? Does it converge robustly enough so that you can actually engage with your approximations later down the line? And this is a convergence of a series. It's of course a well-studied subject in mathematics. Okay, there are tons of theorems, tons of methods, tons of criteria to pick and choose from. So there is really a lot of tools for doing this kind of investigation. But depending on the form of your terms, on your procedure, even this might not always be like the simplest problem to solve. Okay, if your terms are really crazy, it might be really difficult to actually test if it's convergent or not. It might be a question mark, and particle physicists know all about that. They had to deal with infinities popping up everywhere, renormalization group theory. It's whole story. Okay, but so this is something that's important to talk about, to learn about, and we'll try to talk about convergence in more general terms and to show examples how you test it. But it's not always done deal. Okay, it's not you don't always know if it's convergent. Sometimes you have to deal with that. And you can just, okay, I don't know if it converges, but let's hope that it does. Let's work on the assumption that it does. And maybe nothing will blow up in my face, okay? That's also a strategy. But it's much better if you know what are the conditions for the convergence so that you can really be sure about your perturbation series. So the second thing, assuming that we checked convergence and it's robust enough, we have this approximation schemes, right? So we are doing something with our terms, and our hope is that the difference between what we calculate, let's say truncated series or whatever, is the error between this and the exact solution, exact evo, is sufficiently small for our liking, okay? And that would be kind of easy if we had the exact solution in one hand, and our prototype, our approximation, we just take a difference and see if it's big or small. However, since we are doing perturbation theory, probably we don't have access to the exact solution, right? So we cannot just simply compare them. So what to do then? Well, the thing you are trying to do then is you not calculate exactly what is the difference, but to like found some kind of bound on the difference, okay? So you want to like estimate the difference, estimate the error. So we are trying to figure out some easy way, something that can be easily calculated. It's not exactly the difference, it's not exactly the error, but let's say the error cannot be greater than this thing you can easily calculate, okay? So you are trying to estimate your error. And and it's like, this is like important aspect of all this activity here, because if you don't control for your error, you can just write anything. Okay, this is my approximation, but I just have no confidence that it actually reflects the real stuff, right? And don't worry, a lot of physicists do that anyway. It's like, second order approximation, it's probably fine. I mean, I'm sure it's fine. It's okay. Oh, we have cold fusion. Oh, nice. Oh, very good. I mean, this is kind of important to at least have like a ballpark estimate. Okay, if it's completely off or we are on the ball or something like that. And this is like, while checking for convergence of series is something well studied, estimating errors, it's more of an art form. Okay, it's not like an engineering problem with a manual to follow. It's like you have to be inventive to figure this out. Sometimes it's like, I see. Like with, let's say, Taylor series, there is a estimation for error, but it's not always guaranteed. And I will try here to, when we go through different kinds of perturbation theories, I will try to showcase examples when there are estimations, how we get there, how they perform. But it's not always, I mean, they are not always known, okay? But when we can, we will show it. And because I'm speaking about those steps because my idea is like, it's not really to show you examples, just so that you know examples. And let's say, I take this Magnus expansion and I apply to my problem. Rather, I want to give you a fishing rod rather than a fish. Okay, I want to show you how sausage is made so that you can make your own sausage, tailor-made for your own problem. So you have your own perturbation theory. It's a lot of fun doing those perturbation theories. It's really like, I can draw some diagrams like this. It's a lot of fun. Okay, so that would be like an overview of where we are going, okay? But before we get to this whole technical stuff, just generating terms, checking for convergence, estimating errors, and all this stuff. First, I thought that maybe it would be a good thing to do is like maybe convince you why looking at evolution operators is a worthwhile effort in the first place. Why this and not something else? Okay. So my idea is that the first 2, maybe 3, actually, lectures will be, the goal will be there to convince you that evolution operator is the goat, the thing that you want to have if you are doing quantum mechanics, specifically dynamical problems in quantum mechanics, okay? Hence the title, quantum dynamics. And so the first couple of lectures will be basically an introduction to quantum mechanics, okay? So even for those who don't have experience with quantum mechanics but are interested, I know Pamela is interested in that. So this will, I hope this will be like, you will be satisfied after hearing this, and then you can bail out if you don't want the details about convergence of Magnus expansion, whatever. And even if you are experienced you had your courses on quantum mechanics, you're doing quantum mechanics every day, you are quantum mechanic yourself, I think I can guarantee that my takes on this quantum mechanics will be unique enough that it is even interesting for experienced researchers. Because the way I will do it, I will emphasize this difference between quantum dynamics and quantum statics. Probably you never heard this kind of nomenclature, and that's I know you haven't heard it because I just invented it right now, okay? So nobody had it before. But there is this thing, there is this distinction, and then there are parts of physics community, quantum mechanics community that does exclusively dynamics. Well, I will explain what I mean by that. But there are other fields where they do exclusively statics, actually, and you can see how completely different language is used by them. For example, people who do many-body physics or maybe even particle physics, the things they calculate, they are interested in are, I would say, they are dynamical quantities. So they do quantum dynamics. And it's completely like separated from, let's say, quantum information theory, which they are doing statics, okay? Like completely different language. You know, the things that are important for quantum information, like entanglement, locality, the particle physics, many-body physics, they don't care. They never use it because they're doing dynamics, and here they're doing statics, okay? It's kind of like with hydrodynamics, hydrostatics. You want to describe a hydraulic press, right? You use statics. All you need is pressure, volume, temperature, right? And you can explain why the car can be lifted or the brakes work when you press on the pedal. And your system is described by those pressure, volume, temperature. Very simple description. A state, basically, of your system. But you want to describe dynamical situation, how this press actually would work when it moves, you go to hydrodynamics, and it's completely different. Temperature, volume, what? You need viscosity, you have velocity fields, you have temperature fields, entropy generation. It's all completely different ballpark. And it's similar with quantum mechanics as well. Okay, so the introduction I plan to do will be about like elucidating those differences and showing that when you focus on dynamics, the evolution operator is the king, is the thing that controls everything. This is when you're doing dynamical problems, its evolution operator is the thing you have to solve, and then you have everything. Okay. So can we go for a break? Yeah, I think we can go for a break. So that's the plan. Okay, so again, if you are not, you don't think of yourself as a quantum mechanic, okay, someone who actually, Pamela here, who actually wants to do some perturbation theories for practical reasons, but you are interested in what is quantum mechanics, basically. You can stick for the couple of first lectures. Hopefully it will be satisfying. All the questions will be answered there. And then you can just say, okay, I'm done. So it's like two-parter, basically. Of course, if you are still interested, you want to see all the nitty-gritty resolvent methods and Schrieffer-Wolff transformations and all this other crazy stuff, stick around. But the introduction will be kind of separate, but also an integral part of the thing. Okay, so one more thing before we jump into the introduction is like I don't really know I'm not sure like what kind of level of mathematical complexity to engage with. Okay, so I decided that, you know what, I will be like I will explain everything. There will be no stone unturned. If the audience will decide that it's too much, just let me know, so I will skip. So this is why in the notes are those segments. Okay, this is like what is vector space. I'm ready to describe it, But if you're like, oh man, I know what vectors are. Come on, man. So you can, okay, so I just bloop, and I'm next, and just okay, I don't care about this. Here's the bit. Okay, so I will go over everything basically, and just stop me when you feel that it's too much. Okay, and but you know, maybe even if you think you know, maybe you don't. So stick around anyway. And okay, one more thing to say, maybe not. Yeah, I guess that's all. Okay, so yeah, so the level I will try to explain everything basically, and hopefully this won't bore you too much. Oh, but oh yeah, I know the answer. So there will be kind of because I want to also impart on you that for you to be comfortable with mathematics. Okay, don't be afraid of this. So I will be trying to be kind of formal, kind of use mathematical notation, maybe even advanced one, just to make you, you know, to make you comfortable with it, so that you can use it later on. So it will be kind of formalistic and mathematical stuff in this introduction, but don't worry, that will be also a lot of philosophy there. Okay, so there will be also words, not only symbols. Okay, because when we get to the measurement and stuff like that, we have to use words. So I guess that's the point where we can take a break. And after the break, we go to the introduction to quantum mechanics. So, whew, okay, chapter 1. Chapter 1, intro. So I will be trying to, you know, write on the board the same thing that's in notes. So there's a parity there. It's for your convenience. Intro.
What kind of symmetry?
This is just equivalence class. Isomorphism. No, it's not isomorphism.
Isomorphism because the amount is produced, but it would be hopefully it will be
How do you call the morphism that preserves the structure? So it's like homomorphism. Right. I was trying to remember it whole morning, and homomorphism. True. And, you know, once you like start doing some mathematics, like real mathematics, like you prove some theorem or something, you start to realize why mathematicians are like that. Okay, and then you see that, this makes sense. Now I see you're not completely insane. There is a method to this madness. No. There's zero insanity there. It's really just annoying if you haven't done mathematics yourself. No. It's all for promoting discovery. Really, mathematicians, the way they do it, it's completely opaque for someone from outside. So you cannot learn anything from them. Books, it's just nonsense. But once you like start doing mathematics, it's like, now it's so useful. Everything is so useful. So I recommend doing some mathematics of your own. Prove some theorems. Write a paper about theorem. It's an eye opener. And you know and it's also there's also a good practice, because at least I believe that a theoretician, theoretician of physics should be a good mathematician, but also should be a good philosopher, and probably kind of decent programmer, right? It's like So don't be like mediocre in everything. Try to be good at all those things, because mathematicians just have to be good at mathematics. Philosophers have to be good in philosophy, but physicists should be like on the Venn diagram, right? Should be good in everything. Or not, you can still, it still works if you are just humming in everything. All right, introduction to quantum dynamics. So I want to start with controversial way. So I would say that's based on my experience talking to my colleagues and on like the way I imagine how textbooks look like. When people try to explain what is quantum mechanics, they say, oh, quantum mechanics is Schrodinger equation. It's like people usually say that. Quantum mechanics is defined by Schrodinger equation. Okay, so let us define quantum mechanics. So we have our Schrodinger equation. Schrödinger. Let me check if it's recording. It's recording. So, sorry, my paranoia of the streamer. It's not streaming, it's recording. I don't know how to stream.
Once I learn it, will be
Yeah, I mean, to be live, yeah, sure. Schrodinger equation. Oh my, so ugly. But you know what I mean by this squiggly, blah, blah, blah. So Schrodinger equation. So let me write it in this way. So we have a derivative for time, 1 plus imaginary unit, an operator h, and this whole thing acts on the ket t equals 0. That's a form of Schrodinger equation I want to present to you. And that's not all. This is just equation. You have to add initial condition. This is differential equation, so initial condition is required. Condition. And our initial condition will be psi of t0 equals omega, ket omega.
If it is with initial condition, then why we have this index I at psi? Because I believe that then there is just one solution, if we already have specified initial condition.
What? What I? You mean imaginary I?
no. The I, like the index of psi.
It's t.
Oh, okay.
It's
Now
t.
it makes sense. Thank you. Okay.
So this is the conventional we adopt throughout all the nodes. The dependence on time, I will keep it in the subscript. Thank you. Okay. So this is where you look. If you look for time dependence, it will be somewhere in the subscript. Okay. Superscript will be for something else. Okay. So this is a Schrodinger equation and initial condition. Okay. So it's not just equation. There's initial condition, but there is more. There is more. You say, okay, this h here. This is a linear operator that is Hermitian. I will explain it soon. Okay. H dagger H. So this is Hermicity. So H dagger equals H. This is called Hamiltonian. The Hamiltonian. Hamiltonian. And this is the bit that defines the quantum system we are, I guess, describing with this Schrodinger equation. Okay, so this Hamiltonian is the thing that models the dynamical laws in our system. Okay, so you have to specify it, and in this way you identify what is your system. Okay. So I wrote down the Schrodinger equation. So now the question: so can we do quantum mechanics now? Right. So Schrodinger equation is here. Can we do quantum mechanics? And of course, it's not so simple, right? First thing first, you probably have to like decipher what the symbols mean. A cat, the vector, what it means that is a vector. Linear operator, what's linear operator? Hermicity, what's hermicity, where it comes into play? Imaginary unit, okay, I assume everyone knows what, and zero, what is zero? Derivative over time. This I want to explain.
But that zero is, you can zero to vector space, right?
Yes. Yeah. Okay. You can always explain more. Yeah. It is a zero. Ah, right. Well, what equals mean? Yeah. But you know, if you don't want to go, you don't want to. First, you have to invent the universe. If you don't want to go that far back, but at least you know what does this cat, so-called cat vector operators. There's a lot of things to decipher. We will decipher it in a second. But moreover, it's not really so this Schrodinger equation, and this is like typically often physical theories are introduced in this way with some kind of differential equation, right? But the meaning behind such an equation is that it is an implicit definition of like valid state vectors, okay? So the meaning behind this equation is that, so let me write it down. I have here a spiel. So meaning of Schrodinger equation, the meaning behind SE, Schrodinger equation. Maybe I just verbatim write it down here. So it's something like this: a vector valued function of time. I said it will be kind of formalistic, but it is for your own good. Okay, a vector valued function of time. So let me be formalistic then. Oh, wrong button. Oh, wrong button again. I need more pages. Come on, man. Oh, wypisał się. Oh, that's... Zbuferowało wszystko. Buffered everything. So function of time. So let me write it like this. Psi t. Okay. The t is a real parameter, and cat, it sits in a space H. So this kind of math BB font, I don't know how you call it properly, but it's LaTeX is math BB. I will use them to like denote sets or spaces, okay, depending on the context. And this kind of notation to indicate that this is a function, an object function. It's this is the way the mathematicians do it. You can conveniently also incorporate the domains where the objects are, where the objects live. And if you are like not familiar with this, think of lambda functions in programming, Python, C, whatever, or anonymous functions. The idea comes from mathematics, of course. And this is like also the arrow notation. It's also used in many languages. So that's lambda function, the same kind of notation. So let me finish the meaning. A vector valued function of time. So this is time, this is the value, which is a vector. Is a valid, let's call it quantum state. State when it satisfies, oh my God, how do you write satisfy? Yes. satisfies Schrodinger equation, or is a solution to Schrodinger equation. Okay, so this is an implicit definition, right? So we have to like, it's not a Schrodinger equation, it's a solutions of Schrodinger equations that are actually the thing you should be interested in. This is just a compact way to like write down to constraints of what is the form of quantum states that is allowed to describe our system, I guess. And the thing here, so real numbers, that's simple, but this H. This H is something they call Hilbert space. This is Hilbert space. You see, it's like, oh, Schrodinger equation, but there is like, you know, tons of things you have to specify more and more and more. This whole cascade. So when someone says that quantum mechanics is a Schrodinger equation, they mean something else. You know, Hilbert space. Hilbert space. So let me explain what this means. So, one.
It's strange that they call it Hilbert space. They simply should say it's a vector space that is a Hilbert space. So, because a Hilbert space is just a type of a mathematical space, yes?
I'm getting to that. I'm getting to that, what spaces are. So one, we said here that we wrote down the Schrodinger equation. We said the Hamiltonian is an operator. Okay, operators are things that act on something. They have to have some fodder to act on. They act on vectors. Okay, so and those vectors live somewhere in some vector space. So that's why we know by saying that this is an operator, we know that those cats are vectors because they are acted upon by the operator. So we know that those psi t, they live in some vector space. What is vector space, you would ask? We'll get to that. The second thing, so we at least know that there is a vector space. The second thing, they say, I mean, I said that, but that it's a Hermitian operator. But Hermitian, the dagger operation, it's actually, it makes sense, it is defined with respect to an inner product. Okay, it's inner product, scalar product, if you will, something that you do on vectors, right? To be more specific, if you have, let's say you have some operator A, and the operator A dagger, it's defined by this kind of, so let's see, phi A dagger psi. By this, A dagger is such an operator that satisfies this equation. Okay, I will explain this later, right? So a dagger is such operator that satisfies this equation. So in a sense, it's like the dagger is it's like the form of an operator when it acts not on the right, on the vector, but on the left, on the bra, so-called bra. We will explain that later. But this is kind of detail. But the thing I'm getting to is like, okay, they said that it's Hermitian, so we also have to have inner product then. Otherwise, there would be no sense in saying anything about Hermicity. So our vector space is actually a pair. It is a space that is equipped with inner product. So we have, this is what Hubert was saying. So we have vector space where our vectors live, and it's we put on it, add to it a scalar product. So the dots, I mean, I know how it looks like, but this is, imagine that's a placeholder for the arguments. Here you put your vectors. But the pair, vector space equipped with inner product, this is This is what mathematicians call Hilbert space. I mean, with asterisks, there are a little bit more, but we will don't have to go there. So this is Hilbert space. So we see oh my God, I don't know my power.
Double H.
Better?
Super H.
Better. Okay. Let me see if there is one more comment here. Right. So as you can see, so Schrodinger equation is an implicit definition of allowed valid quantum states, but it's also an implicit definition of Hilbert space, of inner products, of everything else, everything around. But it's all implicit. It doesn't give you, in a constructive way, anything. To get something constructive, you have to solve it. But now, I threw around here a lot of jargon: vector spaces, linear operators, inner products, right? And I am prepared to explain all of those.
So in the definition, the word valid, so valid quantum state, so you can ask invalid quantum states and so on. So is it a definition of your quantum state, or define your quantum state using this way, or?
I say yes. This is the, so we have I mean, what valid means, right?
Yeah.
So I guess valid physical, the quantum state that you would assign to the system, let's say in this sense, the state, the function, the state is a function of time. So it's not just one vector, it's a whole function, right? So whole assignment would be a description of state, I guess, under the condition that it satisfies the equation. If it does not satisfy the equation, it might be state for some different system, but not for this system, which is identified by the Hamiltonian that we provided in the beginning. Okay. In this sense, that this is the meaning of Schrodinger equation.
So should you construct the Hamiltonian first, or the solutions first to construct the Hilbert space? What is more commonly?
I guess if you go through the route of Schrodinger equation, you start with Hamiltonian. And I would say this is the route you should take anyway.
Yeah, but Hamiltonian requires the definition of the vector space and Hilbert space.
Yeah, exactly.
It's like cycling.
Yeah, I mean, it's what comes first, right? Yeah, but this is like saying that it's just equation. It's very, very, there's a lot of stuff to unpack here. So let me go just so everyone is on the same page. Let me explain what vector space is for the beginning. So in the notes we are here. So this is the first bit that's skippable if you wish. But if you not wish to do that, let's get into it. So this will be a mathematical aside. Maybe I would also bar vector spaces. Vector spaces. So the V thing. Okay. Oh my God, I'm butchering those fonts so much. So when mathematicians talk about spaces, they mean, and we already seen this here in this example. The space, the Hilbert space, vector space, topological space, Hausdorff space, Banach space, Polish space, whatever else you want. What they mean, how they construct it, they say there is some set of elements. It could be something very abstract, whatever, numbers, maybe numbers, but this is for children. You get something completely abstract, and you add to it, you bolt onto it, some operations, basically. Like here we had a set of vectors, or actually space of vectors, and we bolted onto it inner product. And depending on what you bolt onto stuff, you get different names, right? And vector space is of course constructed in the same way. So in case of in this case, this is a so vector space. You could add over the field f. This f is usually all the either real numbers or complex numbers, but you can go crazy, some quaternions probably, or whatever. But field is a set of scalars or numbers, okay, that will be useful here. And the vector space formally is a triple of things. Like the Hilbert space was a pair, this would be a triple. So one, there is some set of elements as you would, and it will contain all the vectors. So let me pick a familiar notation. So to make sure that we don't confuse them with numbers, I will use arrows here. Okay. Cats are specialized for a reason for quantum mechanics. So in quantum mechanics, we denote vectors as cats, like this. But imagine you could arrow there if you want. But there is a very good reason why we use cats and brass. So, we have things like that. There is more, and they all sit in our container, in our set. The second thing is a operation on vectors, a sum, an addition, which I won't like axiomatize it too much. Just imagine a way to sum vectors. So we would write it like you have something like this defined, okay? And if you want to be like more formalistic, which I want to be, and you cannot stop me. I mean, you can stop me, but it would involve violence. So you would say we would use the lambda notation, okay, which I love so much. So you would say that there is a pair of arguments. You take this pair from E, Cartesian product of E, because you take two, right? Vector and vector, and you map them into a sum of vectors. And the thing about this, it has to live in E also. Okay, so this is a sum. However you defined it, there are some, it is a sum because it has some properties. We won't go into many details here. But the thing is that it's closed, right? So you take two vectors from your set, you add them together, and as a result, however this result is produced, what is the definition of your function of this addition, you will get something inside E. You will also get a vector. It's closed. This is important stuff. So this would be addition. And the third element is a thing like multiplication by a scalar. Scalar multiplication, they sometimes call it, or just multiplication, I guess. And if you, again, want to be formalistic, and I do, so this bad boy here, you would write maybe, again, a pair. You take a pair, alpha and v. Those guys are taken from, alpha is taken from our field. So real numbers, complex numbers, or whatever else you want. Grassmann numbers, I don't know, if you are really, really insane. And from E, right, vector. So we have this kind of pair. And we produce the multiplication. And this, again, must be closed. It's still a vector. However the rules pan out, it must be a vector. Everything is closed. And so this will be multiplication. Maybe scalar multiplication. And this is what, so again, set of things, bolt onto it operation of addition of things, and bolt onto it multiplication by a scalar. This is what vector space is.
Shouldn't it also include the existence of identity and zero, and also the distribution of alpha u plus v would be equal to alpha u plus alpha v? So there are 6, not 3.
It is usually you go, you want some properties of this plus, okay, which is what you say, that there is a zero element on something that when you add, it doesn't change. We want, just intuit it. We don't need to go this deep, okay? But it's a detail, okay? But of course, this addition has some properties, and the multiplication has some properties. But
here we are just looking at the existence of plus and scalar multiplication. The alpha multiplication. Right? We are not interested in the properties per se.
yeah, there are some properties, but I won't spell them out for you. Okay, if you are interested, go to Wikipedia. And they would exhaustively explain you how it's a ring or algebra or some group or whatever you want. You can, mathematicians have spaces, and they also have like higher level constructs, like, and they love the naming stuff. But I also love it, but I have some pity on it, so I won't go into it. So example to see how you eat it. So you can the high school example. I mean, one example would be our quantum states, okay? But to have a like high school example would be a space of arrows drawn on the blackboard or a whiteboard. So vectors like this start from this point, and there are arrows. I can draw like this also. I can draw another one. Ooh, second vector. So this would be V, this would be U. I hope you saw this somewhere, okay? So that would be, so all the arrows I can draw in this way should sit in our set E, contains all the arrows. So it can be, it can be really abstract stuff. It could be functions even. You can, basically, whatever you have, you can make a vector space out of it. Okay, it's like I wanted to say like goulash. You can make it out of everything. I mean, stew, but goulash stew. Just put it into the pot, and you have a stew. Put something into pot, and you have a vector space. So this is our arrow. So we have to now define what we mean by multiplication by scalar and by addition. So multiplication by scalar is is basically scaling your vector. This is how you would define it. So if you multiply it by a number, let's say we multiply v by a number greater than 1, we have to proportionally stretch it. So for example, okay, so this would be alpha v, if alpha is greater than 1. Maybe let's pick another color. Maybe this one. If alpha is less than 1, you shrink it. It's still positive. Where is my cursor? Here it is. Okay, so that would be, let's say, beta v, beta less than 1, but still positive. Okay, multiplying by negative number, you just flip it, right? So that would be v, say, gamma minus gamma. Let's to make sure. Okay, so that would be the scalar multiplication for our vector space. Addition, równoległo boku. Parallelogram rule, is how you call it. Była równoległo boku. I forgot to check it. But triangle. For the difference. Yeah. But which is the addition, but with first you have to negatively scale, right? So the rule is you try to draw a parallel thing to U and parallel thing to V, and you just that won't do. I have a tool. Oop. Okay, that's V plus U. So we have now things to note. The rescaling of arrows produces an arrow, so it's still we stay in our space. The summation, I just drew an arrow, it's closed again. So it's everything is fine. This is a vector space. Hopefully it's not like too boring right now. I mean, I'm having fun, but I don't know, man. Okay, now the interesting part, because this all imposes a very nice structure onto the vector spaces. That's what makes it so useful. Because you look at this picture here, and now you think about it for a bit. And you think, okay, so how big is this vector space of ours? How big is E? This container? How many things are there? And you will quickly realize that it's humongous, because even if you started with only one vector, let's say one arrow, all the multiplications have to be there. So all the scales, right? So it's not. So if you put there one arrow or one vector, there is whole line immediately also have to be automatically included. And that's already continuum size, right? And now you put there another vector. Again, it comes with its own line, continuum times 2. And now all the sums of those guys on the line, it's huge. It's always huge. It will always be humongous. However, it's actually there's only a handful of vectors that really matter, even though it's so huge. But almost all of them are in some way generated by a handful of vectors. Okay, like we said, the whole line, well, it's just one vector and all the multiplications, just generate them, right? So this leads to the idea of so-called span, not spam, span. So you have, so let's say if you said so span of V. I don't know. So this is a span of V would be all the multiplications that you can come up with. So let me introduce my other convention of notation of sets. So set will be in curly brackets. Does Python use curly brackets for sets as well?
No,
Square.
Curly brackets for dictionary.
No, curly brackets.
I see. That's good. And tuples are. We'll get to Python soon. I'm just checking because I'm amateur in Python. Yes, exactly. And they are unordered. Sets are unordered. And this is no accident, of course. So this is a useful mental trick I like to employ. When you want to imagine someone comes in and writes a span. So he said, so this is a set of this kind of things under the condition. So this will be the list of conditions after the vertical sign. And the condition is that you take all the scalars from your field, all the real numbers. So you can think about it, you had imagine it, how would I implement it in my favorite programming language, for example, right? So this is like with Python already has sets, which is nice, and you can, okay, sets have, I'm creating sets, let's use set has this property, unordered, this is not ordered, I didn't impose any ordering here. It's only unique things. So basically, if you put many copies, they would just collapse into one. That's how sets work in mathematics as well. Very useful trick. So span. So basically, we say we take some vector and generate whole subspace, something that sits in our subset of our vector space. Now we can continue with this construction. We could take different vector from our space, but such that it's not spanned by V. That is, you could say there is no such number alpha. So let's say we take U. Okay, we take U. So U is such that there is no such number alpha that U would be equal to alpha V. Okay? If such number doesn't exist, then it cannot be in the span. And we can see optically that it's not, because span is this line, parallel line to vector. No, this is, okay, more or less this is a span, okay? U is not in there, okay? It's a different direction. So you could phrase it formally that there is no such alpha that this equation is satisfied, but there is a better way. Mathematicians came up with a better way of phrasing this. The better way they came up with, they say the idea of linear independence. So, oh, I didn't switch back. Linear independence. So they say, consider equation alpha V plus beta U equals 0. Okay? And V and U are linear independent, or U is not in the span of V, and also V is not in the span of U, because this is like, when this has exactly one solution alpha equals beta equals 0. Okay, the only way to satisfy this equation, if they are not in a span, each other spans, is to put everything to 0 identically. Okay, if this equation has only one solution of this kind, you say that those V and U are linear independent. You can imagine that this definition is very nice because you can add more vectors later. Okay, and the same kind of condition imposed on it. So we picked U. It's not in a span. V is not in the span of U. They are independent, but all other vectors are dependent, linearly dependent. In other words, if I took a sums of vectors from those two spans, right, I will span the rest of my space, basically. Right? So let me write it like this. Span V and U. So I take two linearly independent vectors. So this will be a set. Let me write it like, of course, formalistically, because this is what I do. So let me write it like, maybe like this. PU, such that AV is an element for span from span V, okay? And BU is taken from the span of U. That would be a very, so I take from vector from this line, and just add them together, which will produce something like this, for example. But this, of course, this maybe not, of course, maybe you don't see it immediately, but using what the span of V and U is, you can just simplify it immediately and say that this is just a where alpha, beta are in F. This is the same as saying this. So basically, all the combinations, linear combinations of linearly independent vectors. They span, in this case, all the arrows I could imagine on this, I could draw here, are like this, which you can probably see it if you don't just try to draw it, and you will see it. Okay, so I could, if I looked for another vector that is like linearly independent of those two, I would have to go outside of the plane, right? The third dimension. I would have to add another dimension. And then again, I will get another span from this third dimension, and then combine all the VU and let's say W, and then I will get a span of everything else in the whole volume, right? Not only in plane. So in other words, even though, okay, so this, so let me define something. So linearly independent then set. So that would be a set of vectors such that, say, V1 up to some Vk or Vd. So Vd is better. Vd, such that when I write down the equation, alpha d Vd equals 0, there is only one solution, and the solution is that all the coefficients are 0. Only one solution. So this is a direct generalization of what we said before. Equals alpha d equals 0. Okay, if you do it like this, you have your set of linear independent vectors. And now, if this set is maximal, which means that there is any other vector from your space is not linearly independent of this set. In other words, every other vector is some combination of those vectors here. The span of this maximal set is the whole space. So if this one is maximal, then we get that span of all those guys, Vd, is equal to V. I hope it's not too simple for you. And then in that case, you say this set of linearly independent vectors is basis. You call it a basis. It's basis, yeah. Because all the space is based on them. All the vectors, I mean the number of those, this maximal number of those linear independent vectors, D in this case, is called the dimension of the space, okay? And all the other vectors in V can be expressed as a linear combination of these basis vectors. So if you take some arbitrary vector A, it will be possible to write it like this kind of sum. K, maybe let's add here superscript V, Vk vector. So these are scalars, right? And for every vector, these scalars are unique. Okay, every vector has a unique set of scalars. and they call them coordinates, usually. Coordinates of a vector A in a basis V. Let's call it V, because we use letter V for those vectors here. And same with some vector B would have its own set of coordinates, some B, K, V, V, K, and so on, any vector. And any operation that you might want to engage with your vectors, once you have chosen this basis, it basically simplifies to some operation on coordinates. So if I want, let's say, alpha A plus beta B, I just decompose them in my basis. So I have alpha sum AK V K plus beta sum K BK V vector. And this I can simply collect the terms proportional to the basis vectors. And I get K from 1 to D, the dimension, and just alpha A K V plus beta B K V VK. Easy, right? You just do the simple arithmetic on the coordinates once you choose the basis. However, the choice of basis is never unique. Okay, there are infinitely many choices of linear independent maximal sets. Some might be better, some might be worse. It depends on your criterion. But whatever the choice you make, so let's say we have a span on V's, V1 to VK, VD, sorry, versus span on some other set, let's say U1, UD. The thing that they will have in common,
Rule number 15. Yes.
okay, so many people, man, that's so cute.
Only problem.
The only problem.
Yes, I'm experienced with squeezing.
How are we on time?
I'm usually squeeze spins, but I can try also with
Yeah.
humans. If you give me a large enough quantum operator, I can squeeze humans as well. You have a total squeezed human, collective human squeeze. Socialism. We are not anti-communism.
Okay, so we have one basis, other bases, they're not the same. The collection is different, although in each case they are linear independent. And of course, once you pick one basis, you can express the other basis as a linear combination of the first one, and vice versa. And the same you can do with any other vector, like A and B. So I can write my A dude as a sum K. But whatever the choice of basis, the thing in common will be the number, this maximal number of vectors. That's why this D, this number, the dimension, is like a property of the space. So so even though the vector space is huge, it's actually only D vectors that matter. Okay, so it's very small. Unless the dimension is infinite, then it's hell. But we won't talk about that. We don't want. Oof. That's oof.
In real life, it's like usually.
I disagree.
We have different real lives.
Maybe. So let me write this K V. That's why I use the superscript VK. But you could also decompose it in the other basis, AKU. And the coefficients are unique, but unique per basis, okay? So the set AK with V superscript, there are D numbers there, but those numbers are not the same as numbers AK with superscript U, okay? But they are related to each other because, like I said, you can decompose one basis in the other basis, right? So I could decompose U in V, for example. So I could just carry on with this and say, okay, so here I have sum over K. I have my coefficients U, but vector UK, well, it's some combination of let's call it U. Maybe let's call it how do I chose to call them? Like this. K L V L coefficients. Those are special coefficients because they are bases, relate to bases. And this I can just rearrange stuff and write it as K over, L D sum over K, 1D, A, K, U, U, K, L, V, L. All right? And because of the uniqueness of the decompositions, we get the formula for basis transformation of vector coefficients. So EKV equals sum K1 D A K U U K L. All right? So to produce a coefficient, the coordinates in some basis, when you have coordinates in some other basis, all you need to do is to know the coefficients of decomposition of basis U into basis V, for example. And with those, you can calculate this sum here. And this is how you, so this is a same vector, but with different representation, so depending on the choice of basis. Wow, that's all for vector spaces. So let me finish this with, oh, it's actually on time. So now that was a lot of bullshit, okay? A lot of talking, a lot of mathematics and stuff like that. So again, if you want to imagine this stuff, because there is a structure that can be imagined, okay? It's cool, you know. I didn't have to consult my notes too much. I just had it in my mind. So if you want to like be familiar with this kind of stuff, again, think how would you implement vectors in Python, let's say. What would you do? Okay, and then this will give you some better idea what this thing actually is, what this vector space is. So I'm not a Python user very much, but I imagine you all are Python users. Is it true? Everyone knows Python. Right? I know that a little bit, but I know the syntax. If I'm mistaken, you can correct me. So I thought I would just write some pseudocode for you to imagine. I don't know if it's a good move. I thought it's kind of cute. So I would say if you want to implement vectors in Python, you would have to define some objects, classes. You know classes? Everyone should know classes, right? So I would say that you write it class, right? Class name vector and semicolon. No semicolon. but you do the tab, right? The indent to have a. Even when you define class, it's like.
No, you would do the kropek. No, Python doesn't have it. I mean, but it is okay. It's not Python. It's pseudocode. So it's pseudocode actually doesn't matter.
Okay, whatever. You can imagine. So now let's say so we have the constructor for our objects. So that's constructor. I think in Python it's init. Okay, and parentheses, right? Self, right? Because it has to have reference to itself, to object to itself, right? It's kind of weird. Nobody does that except Python. And something, right? And the other parameter. So let's think. How would we implement this guy? What kind of fields this object has to possess? So, the vector spaces. Maybe they are big, but we know that there is this handful d important vectors, right? And then every vector is just a tuple of coordinates. If we choose a basis, so let's internally choose some basis. We won't tell anyone what it is. They don't need to know. But for the purpose of implementation, let's choose some. And then to completely specify our vector, we just need to give the tuple of coordinates, right? So the argument would be some tuple of length d. So let's, I don't know, a, like this. Okay. By it, tuple of some length d, whatever. So the initialization would be simply to self dot, let's call this field coords, right? And just a. Okay? You need semicolons? Do you use semicolons? No. Such a weird language. So that would be our. It's a. Can you do private fields in Python? Okay, maybe you can. But it's an internal thing. You don't have to know about it. Vectors just have to know about it. What basis you chose. And now, okay, so that would be our object. What this object has to be able to do, we have to add and multiply. So well, we can define the methods. Def for method. So mult.
Proper init also that and
Very good, very good. Mult self. Okay, it will be, we're multiplying the vector, so the vector has to know how to be multiplied, and some number, so alpha. Can you control for type?
no.
There's no, it's not converged to that.
Okay.
It's more of a for you than.
Okay. So I won't.
There are assumptions, but still everything is fun.
Okay. Oh my God, whatever that means. So how would we implement multiplication by scalar? Any ideas? Yeah, just multiply all the tuple by every element of tuple by a number. Does Python understand this? Self chords. Does it understand something like this?
Not that it's
That works, but only for numbers.
So imagine that we imported a package that understands it. All right?
if we import the package that understands, then we just have vectors. We don't need to make a class for that.
No. Vector is a tuple internally. But from outside, we don't know that it has some tuple inside. We just know that it can be multiplied and added with other vectors. That's the trick. That's the trick for your imagination. We don't know on its own the vectors, we don't have access to the coordinates. We have to define some additional structures, additional operations to actually access this. We just know that how to add vectors and how to multiply them by scalars, but that there is underneath there are coordinates. We don't know them. Okay, we would have to add more operations to actually get access to specific coordinates. This is where the inner product will come in. But for now, the last thing to do would be plus self and some other vector, u. So this should be vector also. I don't know. Something like this. This is how you control for type. Okay, very good. So how do we implement addition? Yeah, exactly. Add the tuple of u to the tuple of this object, right? Chords. Can it be like this? Tuple to tuple. I don't know. We downloaded the package, whatever. It knows how to handle it. And that's. I don't know.
Oh yeah.
I don't know. But so you can cogitate about that, but that's that's basically that's all you need. This is vector. This object is a vector, okay? And imagine that it's protected. I mean the field, the coordinates are protected, so you cannot access them directly. You just know the method multiplication and plus. You can add vectors. Well, we could also add a static.
I can't feel that Python is the worst language to build pseudocode.
Okay, I don't know, man. One more thing that we would probably need, if you cannot access coordinates, at least you have to know how to like equate vectors. Okay, something we use that. We use that, right? The sum of vectors equals 0, right? That's a equation. So there has to be a method for checking if two vectors are the same or not, right? So we have to have something for that. But this could be a static method. You know what static methods are? It's not on the object, but on in the class. Yes. Equal. Without self, it just needs two vectors, vu, all vectors. And what it would produce, it's simply, how do you check if two vectors are the same? Yeah, I mean, it returns the answer that v chords equals u chords. So true if they are the same, false if not. And this is vector space in Python. We have special packages, right? So hopefully this wasn't too much mathematical details. We are not done yet. Next time we will be more, and then we'll get to some philosophy. Okay, so that would be this for this week.